about aircraft instruments, and let's start off talking about instrument cases and their range markings. Now, the instruments that you've got in aircraft, both flight instruments and also engine instruments, should be marked and graduated. They've got colored arcs, colored lines, and so on them. And the way that they're marked and graduated is in accordance with the specific aircraft maintenance or flight manual. In other words, the manufacturer tells you exactly where the different colored arcs should be and so on. The reason that the aircraft instruments are color-coded is to direct your attention, as the FAA says, to approaching operating difficulties. What that basically means is that for engine instruments, you'll have colored arcs, green arcs for normal operating range, yellow arcs for caution areas, red lines for you don't want to operate above or below this as far as temperature or pressure is concerned. And also on the airspeed indicator, you've got color-coded arcs. And the reason is so that the pilot has, at a real quick glance, information about whether he's operating in an area in a spectrum where he should be. Now, those aircraft instrument range markings, as the FAA calls these colored arcs, are specified by federal aviation regulations. It's not just a case of the manufacturers got together and said, let's do it this way. The federal aviation regulations require that those range markings, those colored arcs, be on there. A couple of instruments that you'll see that have those range markings on them are the airspeed indicator. Notice we have white arc, green arc, red lines, yellow arc, a blue arc, and so on there. And also another place you're going to find it is the cylinder head temperature gauge. Temperature gauges very typically have those colored arcs also. In this particular case, we've got an oil temperature gauge, and notice that we have red lines on the bottom and on the top, and then we've got a green arc for where our normal operating temperature is going to be. The green arc on an aircraft temperature gauge indicates the desirable temperature range that we want to be operating in. If you have a red radial line, what that red radial line indicates the maximum or minimum safe operating limits. On an airspeed indicator like this is the maximum airspeed, the never exceed speed for operating the aircraft at. On temperature gauges, it would be the maximum temperature that you would want to be operating the engine at. So the red radial line on any instrument indicates the maximum, or if it's on the bottom end, the minimum safe operating limits. Now, airspeed indicators for twin-engine airplanes have, among other markings, a blue radial line. And what that blue radial line indicates is the best rate of climb speed with one engine inoperative. On a multi-engine aircraft, it's very important to know very quickly what the best speed is, the best rate of climb speed, if you have an engine failure. And they don't want you to have to look it up in a book or search for a placard, so they mark it right there on the airspeed indicator with that blue radial line. Now, on most instruments, these colored arcs and radial lines are marked on the face of the instrument itself. But sometimes the colored arcs, for one reason or another, will be marked on the glass rather than on the face of the instrument. And if they mark it on the glass, what they will also have is a white index mark on the instrument, and that white index mark would be used to indicate whether the cover glass has slipped. Because if you put the colored markings on the glass and then the glass slips, then the colored arcs will not be lined up properly with the various speeds that they're supposed to be representing. So they use a white index mark, if that's the case, to tell you whether the cover glass has slipped any in the instrument. Now, when an instrument is being installed in an aircraft, the person who's responsible for making sure that it is properly marked for that particular airplane is the instrument installer. So the instrument installer has got to make sure that it's properly marked, properly labeled for the particular airplane the instrument is being installed in. If you have electrical instruments are typically going to be mounted in an iron or a steel case, and the reason for that is to prevent interference from outside magnetic fields. The iron or steel case around the instrument will help prevent interference from outside magnetic fields. Now, one of the things the FAA wants you to know about instrument cases is that if you have a de-icing pressure gauge, the case for the de-icing pressure gauge telling you how much pressure there is in the de-icing system, that case will be vented to keep the interior of the case at atmospheric pressure. So a de-icing pressure gauge case will be vented to keep the interior at atmospheric pressure. Now let's talk about some maintenance on aircraft instruments. If you've got an instrument case that has the paint chipped on the case, that's no big deal. That's just a cosmetic thing. It is acceptable and it would not require any corrective action by a mechanic. There are some instrument discrepancies, instrument problems that an aviation mechanic can correct. That would be things like the mounting screws are loose, the paint on the case is chipped. You don't have to do anything about it, but you can touch it up if you want to, or if the aircraft owner wants you to. If you're leaking, got a leak at a line B nut, or if there's a red line missing on an instrument. Those are the types of discrepancies that an aviation mechanic can correct, because these do not require going into the instrument itself. The red line missing, for instance, you can paint just on the outside on the glass of the instrument itself. So an aviation mechanic can correct those. But there are some instrument discrepancies that would require replacement of the instrument instead. Discrepancies that would require instrument replacement would be the case itself is leaking. The glass in the instrument is cracked. The instrument will not zero out, or the instrument is fogged. These kinds of problems will require replacement of the instrument, and they're not the type of thing that an aviation mechanic can work on. Now, a certified mechanic can perform 100-hour inspections of instruments. You are allowed, and indeed you must, inspect the instruments when you do various inspections and see whether the instruments look like they are complete and whole and whether they're functioning properly. However, a mechanic, even if he's got an airframe and a power plant rating, may not perform repairs on aircraft instruments. A mechanic cannot perform repairs on engine instruments, or for that matter on flight instruments. That has to be done by a repair shop. So basically what the mechanic does is inspect the instruments, sees if there's any problems, and if there are problems which would require taking the instrument apart in order to fix it, then he's going to simply have to replace it and let a repair shop do any repair work or overhaul on the instrument that needs to be done. Because repair of an aircraft instrument can only be done by a certificated repair station that is approved for that class of instrument. An aviation mechanic cannot repair instruments. Only a repair station can do that, and they have to be approved for that class of instrument. Okay, let's talk about the instrument panel. The panels that you mount the aircraft instruments in are usually shock mounted, and the reason for that is to absorb low frequency, high amplitude shocks. And you need to remember those two words, low frequency and high amplitude, because those are the type of shocks that you put the instrument panels on shock mounts in order to absorb. Now, how many shock mounts are you going to have? Well, the number of shock mounts that are needed for an instrument panel installation is determined by the weight of the complete panel unit. And by complete panel unit, that includes the instruments, but it also includes all of the sheet metal and so on. So the weight of the complete unit is what determines how many shock mounts you're going to need. That aircraft instrument panel, by the way, needs to be electrically bonded to the aircraft structure. And the reason that it is electrically bonded to the aircraft structure is not to keep it from bouncing around, that's done by the shock mounts, but it's to provide current return paths. That's the reason for electrical bonding. Now, the way that aircraft instruments are mounted in their panels depends on how the instrument case is designed. If you've got an instrument like this vertical speed indicator that has a flange on it, then what you use is mounting screws going through that flange. But sometimes what you'll have instead is a flangeless instrument case, and we've got a sample of that here in this radio case. Notice that there is no flange around it, and if you have a flangeless instrument case, the way it's mounted in an instrument panel is there is an expanding type clamp that is secured to the back of the panel. You slide the instrument in, and then you tighten that clamp around the instrument, in this case around the radio, by a screw from the front of the instrument panel. So with a flangeless instrument case, what you've got is an expanding type clamp on the back of the instrument panel, and that clamp is tightened down around the instrument by a screw, and you do that from the front of the instrument panel. Let's talk about the altimeter and the other instruments that are connected to the aircraft's pedostatic system. There are 3 flight instruments that are connected to the pedostatic system, and those are the altimeter, the rate of climb or vertical speed indicator, you'll see both terminologies, and the airspeed indicator. The pedostatic system has a static vent on either side of the fuselage joined together in a Y, and the reason you've got one on either side is so if the plane yaws one way or another, the increased pressure on one side will be made up for by the decreased pressure on the other. So you'll have a pretty good accurate reading of ambient pressure. They join together and run forward to give static air, static pressure to the altimeter, the vertical speed indicator, and the airspeed indicator. Now notice that the airspeed indicator is the only one of these that has ram air coming in through the pitot tube. And what the airspeed indicator is doing is taking this ram air coming in through the pitot tube and comparing it against the ambient or static pressure air, and the difference gives you the airspeed indication. On the vertical speed indicator and on the altimeter, they're simply sensing the ambient pressure, ambient pressure air, and telling you whether you're climbing or descending and giving you your altitude above mean sea level. Normally is how the altimeter is set to give us our altitude. So there are 3 instruments connected to the pedostatic system: the altimeter, vertical speed indicator, and airspeed indicator. But suppose the FAA asks you which of these instruments are connected only to the aircraft's static pressure system. There are 2 of them that are only connected to the static pressure and not to the pitot or ram pressure, and those 2 are the altimeter and the vertical speed indicator or rate of climb. The airspeed indicator is connected to both the ram air, the pitot air, and the static air pressure. And by measuring the differential, as I said, between the pitot pressure and the static air pressure, it will tell you what your indicated airspeed is. Now, both the ram air and the static air are external air sources outside the cabin of the aircraft. So cabin air pressure has no effect on the airspeed indicator whatsoever unless you have a certain kind of problem. Suppose that you have a pressurized aircraft. And the static pressure line became disconnected inside that pressurized cabin during cruising flight. The question is, what will happen to the altimeter and the airspeed indicator if this static line becomes disconnected in a pressurized cabin? Well, the whole idea of a pressurized cabin is that while you may be flying at, say, 20,000 feet, you'll only have a cabin altitude of, say, 6,000 feet. It's pressurized to give you a lower cabin flight altitude. If the static line becomes disconnected in the cabin, then it's going to be filled with air at the cabin pressure, which is a 6,000-foot cabin, and not the external air pressure of, say, 20,000 feet. So if you have pressurized air inside the static vent from a pressurized air cabin, what will happen is that the altimeter will read the same as the actual cabin altitude, not your flight altitude, and the airspeed indicator will be wrong. The altimeter will read low because the cabin altitude is 6,000 feet instead of 20,000 feet, so it'll read 6,000 instead of 20,000. The airspeed indicator is taking the ram air coming in here and comparing it against the air in the static vent, but if the air in the static vent is pressurized cabin air, it's going to be a much higher pressure than you would expect, and the difference will be much less, and the airspeed indicator will read low. So if the static pressure line is disconnected inside a pressurized cabin in cruising flight, the result you'll get is that both the altimeter and the airspeed indicator will read too low. Now the static system, the pitot-static system, has to be tested and inspected according to regulation. The regulation that requires it is FAR 91.411. But the requirements on how to test it and how to inspect it, they want you to know where to find those, and you find those in FAR Part 43, Appendix E. FAR Part 43, Appendix E is what tells you how to test the static pressure system on an aircraft. One of the things that it tells you is that when you're performing the static system leakage test, what you're using is suction, or as they say on the test, negative pressure. You apply suction in the static lines, and what you're doing is you're checking for leaks. Does the system leak? Will it hold the suction without giving erroneous readings? If you test this system for leaks in compliance with the system, you can do it one of two ways. You can use a pitot-static system tester that has altimeter and VSI indication, or you can actually use the aircraft altimeter instead. What you do is you apply the suction onto the static system and you watch and see what the aircraft altimeter does. You apply a suction to an equivalent altitude, and they'll tell you on the tester exactly what that equivalent altitude is, and then you hold the system there and you look for the rate of change on the altimeter. What you're looking for is, does the altimeter move when you're not actually changing the suction? And you want to know by that will tell you whether or not you have a leak. The maximum altitude loss that is permitted when you're doing this instrument static pressure integrity check, leak check, is 100 feet in 1 minute. So if the altimeter is showing more than a 100-foot change in 1 minute, then you've got excessive leakage in that instrument system. Now, if the static pressure system does show excessive leakage, how do you locate it? You locate the leaks by going in and isolating different parts of the line, and then you test each portion systematically, starting with the instrument connection, to try and figure out exactly what segment of the lines, what segment of the connections that leak is located in. Now, they want you to be familiar with the concept of pressure altitude. A barometric altimeter like this will indicate pressure altitude whenever the scale on the altimeter is set to 29.92 inches of mercury. And it doesn't make any difference whether you're on the ground or in flight. If you go to the setting window on the altimeter and you set it to 29.92 inches of mercury, the altimeter will be telling you your pressure altitude. And that's important because you use it for some diagnostic information and also as a pilot to find out how the aircraft is going to be performing. A different type of altimeter other than the barometric altimeter is a radar altimeter. And what a radar altimeter does is it transmits a signal from the aircraft which goes down to the ground and is reflected back to the aircraft. And the instrument analyzes that signal and says, okay, I am 100 feet, 500 feet, 800 feet, 1,000 feet above the ground. So rather than knowing your altitude just above sea level, the advantage of the radar altimeter is it tells you how high you are above the ground that you're passing over at the moment and helps an awful lot in obstruction clearance. Now, one of the flight instruments in the cockpit is a turn coordinator, and the turn coordinator tells two pieces of information. It tells about roll and it tells about yaw. As far as roll is concerned, it tells you whether you're rolling into a left-hand turn or whether, as in this case, you're rolling into a right-hand turn. Notice how the right wing of the aircraft goes down, showing a right-hand turn. So that's the roll. The second thing, as I said, is the yaw indication, whether the nose of the aircraft is yawing to the left or to the right, and it does that with this ball and the tube down here, and it does that by having the ball out to one side or another, depending on which way the nose of the aircraft is yawing. What the turn coordinator does not tell you, and it says right on it, is no pitch information. It does not tell you whether the nose of the aircraft is pitched up or pitched down. What it does tell you is roll and yaw information. Now, when you look at all of the flight instruments in the aircraft panel, in addition to the turn coordinator that we just talked about, there's two others that are gyroscopic instruments controlled by gyroscopes, and that is the attitude indicator and also the heading indicator. So there are three instruments total. Need to remember that number, three of them, that are controlled by gyroscopes. The attitude indicator, which is often called the artificial horizon, the heading indicator, or the directional gyro, which tells you which direction the airplane is flying, and in older instruments, the turn needle of the turn and slip indicator, which works just like the turn coordinator, but has a needle instead of a little airplane. Now, on the directional gyro or heading indicator, there's a lubber line on there. It's this white line on this particular type. Sometimes it'll be a line coming down from the top, but that lubber line is used to represent the nose of the aircraft. So whatever heading the aircraft is on, whatever way the nose of the aircraft is pointing, will be right under or at the point of that lubber line on the directional gyro. Now, the heading indicator and the attitude indicator are normally vacuum-operated instruments, and the vacuum system is very touchy as far as needing clean air is concerned. They have dry-type vacuum pumps with carbon vanes very commonly, and those dry-type vacuum pumps with carbon vanes are very susceptible to damage. What they have to have is good filters on them. Here's the master filter for a vacuum system. They are very susceptible, the pumps are very susceptible to damage from solid airborne particles, and they have to take in only filtered air. They need a good filter on there to make sure that they don't get contaminants in there. Now, if you're looking at a vacuum-operated instrument and you find that the glass is loose on that instrument, can you as a mechanic repair it? No, you're not allowed to repair instruments. You're going to have to install another instrument, because remember that only instrument shops are going to be able to work on the instruments. A repair station that's licensed for that class of instrument is going to have to do the repair. What you're going to have to do is install another instrument. Now, the condition that is most likely to cause excessive vacuum in a vacuum system is the vacuum relief valve not being properly adjusted. If the vacuum relief valve is improperly adjusted, then you could end up with excessive vacuum. You set it for what the system pressure ought to be, and if it's not set properly, then you can get too much vacuum. Now, this is the wave of the future on instruments, the electronic flight Instrument System. An electronic flight instrument system, or EFIS, uses sunlight-readable CRTs like this in order to display data and also representations of aircraft instruments. By using the EFIS, they eliminate all kinds of mechanical instruments, and it relieves pilot workload and instrument panel clutter, because the advantage of an EFIS like this is it only displays the information that you need at the time, and you can change what is displayed on it, and if you have some kind of mechanical problem with the aircraft, then and only then will the appropriate instruments and gauges and so on show up on the CRT. Now, there are 4 elements in an EFIS system, and you need to know this for the test. The elements are the CRT display, the symbol generator, the display controller, and the source select panel. The CRT display is the screen that we've been looking at. What happens is that data that is transmitted between the different components in the EFIS is converted into digital or alphanumeric signals. That data is then displayed on the CRT, the cathode ray tube, and it's displayed as both alphanumeric data and also as representations of aircraft instruments. In other words, you'll actually see a symbol, a picture of a particular aircraft instrument, or you will see alphanumeric data depending on exactly what you need to be looking at the moment, and that's all displayed on the CRT. You also have in there a symbol generator. A symbol generator receives and processes the input signals from the aircraft and engine sensors. So it takes in this information and it processes it, and then it sends the data out to the appropriate display. That's what the symbol generator does. They will ask you on the test, what is the function of these different components? The function of a display controller in the EFIS is to allow the pilot to select the appropriate system configuration for current flight situation. In other words, sometimes you want to look at certain types of flight instruments, sometimes you want to look at certain types of engine instrumentation, and the display controller allows you to select whatever configuration, whatever information you want to be looking at for the current flight situation. Let's talk about our temperature indicators. First of all, exhaust gas temperature gauges. Exhaust gas temperature gauges tell you what the temperature of the air is going out the engine exhaust. Now, if you're measuring turbine exhaust gas temperatures, then you've got to use some special thermocouples. Chromel, Alumel, thermocouples are used for turbine EGT, exhaust gas temperature measurements. And by the way, thermocouple leads are designed for a specific installation, and they cannot be altered, because if you alter them, if you change them, you're going to change the electrical currents in them, and then they're not going to work the way that they were designed to do. Now, let's assume that instead of measuring EGT, what you want to do is measure something like the oil temperature in the engine. You're going to use a different type of temperature indicator to do that, because you're working with much lower temperatures than if you were measuring EGT. The type of temperature indicator that you would use for oil temperature, as well as some other things we'll talk about, is a resistance type temperature indicator. Using a Wheatstone bridge or ratiometer circuits, a resistance type temperature indicator can be used to indicate the temperatures of things like free air, carburetor air, engine coolant, or, as we have in this gauge, oil temperature. The reason that you use resistance type temperature indicators for measuring these kinds of temperatures is because they are much lower temperatures than EGT or CHT, than the exhaust gas temperature or the cylinder head temperature, and thermocouples will not work at these much lower temperatures. The FAA will give you a list on the test and ask ask you what types of temperatures can you measure with resistance type temperature indicators. What you can measure is things like free air temperature, carburetor air temperature, engine coolant temperature, or oil temperature. What they want you to know that you cannot measure with resistance type temperature indicators are things like exhaust gas temperatures, EGT, and cylinder head temperatures, CHT. Now, when you have aircraft like an MU-2 that have hydraulic systems in them to operate various components, you're going to need to have hydraulic pressure gauges to tell you what the pressure is in that hydraulic system. And the hydraulic pressure gauges will typically be a Borden tube. And with a Borden tube, basically what you've got is a tube that will tend to straighten out with an increase in pressure or in temperature, and that drives the indicating mechanism. So a Borden tube instrument like this can be used to indicate either pressure or temperature, either pressure or temperature, as in a pressure as in a hydraulic pressure gauge, or it can be used for indicating temperature. Now, the manifold pressure gauge on a reciprocating engine is measuring the atmospheric pressure inside the engine manifold. And when the engine's not operating, what it's basically going to be showing is existing atmospheric pressure. Existing atmospheric pressure would normally be about on the order of 29.92. That's about what this manifold pressure gauge is showing. So when the engine's not running, what that gauge is going to indicate is simply the existing or ambient atmospheric pressure. Now, let's talk about the magnetic compass in the aircraft. The magnetic compass bowl here is filled with a liquid, and the purpose of that liquid is to dampen the oscillation of the float. The float is what actually has our directions or headings on it, and it's floating in a liquid there that will dampen its oscillations. And again, this line on the magnetic compass is called a lubber line, and the heading of the aircraft is going to be showing up under that lubber line. That fixed reference marker attached to the compass bowl is called a lubber line. Now, because the magnetic compass is supposed to show you your direction relative to magnetic north, you want to make sure that you stay away from any magnetic items, keep any magnetic items away from that compass, particularly anything that's going to stay with it. So cotter pins, if you're going to use them in close proximity to a magnetic compass, need to be made of corrosion-resisting steel. What you don't want to use is anything magnetic, because that's going to throw the compass off. So use cotter pins of corrosion-resistant steel in proximity to that magnetic compass. Now, a magnetic compass is swung at various operating intervals, specified operating intervals, by you as a mechanic, and the reason for swinging the compass is to figure out and compensate for magnetic influence or compass deviation. There are magnetic fields in the aircraft put up by the engine and various other components of the aircraft, also magnetic fields from the radios if the radios are on, and those are going to have an influence on the compass. And so what you try and do is adjust the compass, and there are magnets that you use to do that, so that it has the minimum amount of error that you possibly can. The maximum deviation that is permitted during level flight is 10 degrees, meaning the difference between the heading you're actually on and the heading that the magnetic compass says you're on. And so you use adjusting magnets in order to try and get that deviation or error out of the compass. Maximum deviation is 10 degrees. Now, what you were hearing there was a stall warning system. A stall warning system is designed to begin warning the pilot when the stall is imminent but has not yet started. Notice that this wing is tufted and that the yarn on it is basically still all aligned with the airflow, so that audio on it told us on the stall warning, told us that a stall was imminent. We were close to it, but it had not yet started. Now, if you don't do anything about it, if you let it keep on going, you will eventually get a stall, and what you're going to see then is, if you had a wing tufted like this, the yarn just goes all over the place as the aircraft stalls. Now, how does the stall warning system actually work? Well, one type of stall warning system is a pneumatic or reed type stall warning system, like on this Cessna. It's activated when the angle of attack is increased to the point where you actually have negative air pressure inside the slot. And that negative air pressure, you need to know it's negative air pressure, not positive or ambient air pressure. That negative air pressure allows air to flow through the reed and out the slot, and it creates an audible warning indication that sounds like this. Now let's talk about the angle of attack indicating system. The angle of attack indicating system is a very useful system. You find it on jets and also a lot of turboprops, some of the smaller aircraft. And basically what it does is it measures the angle between the local airflow around the direction detector, which is this unit right here, and the fuselage reference plane. What it's telling you is what kind of angle is the aircraft really at as far as how that aircraft is performing. What is the angle of attack of the aircraft? And it can be a much more useful piece of information than just knowing what the airspeed of the aircraft is, because it tells you more about how close the aircraft is to a stalling condition. So the operation of that angle of attack system is based on measuring pressure differential at a point where the airstream is not flowing parallel to the true angle of attack. This is the chord line of the wing here, and this is the angle of attack indicator, and basically what it's doing is it's measuring the difference between the way the wing is pointed and the way the aircraft is actually moving, and that's giving you your angle of attack and telling you how close the aircraft is to stall. Extremely useful as far as figuring out the performance, particularly on a jet. Measuring pressure differential at a point where the airstream is not flowing parallel to the true angle of attack of the aircraft. Let's talk about now synchrotype remote indicating instruments. Now that's a mouthful, synchrotype remote indicating instruments, but basically it's an electrical indicating system used for transmitting information from one point to another, where you've got a transmitter connected to a receiver electrically with wires, and that's the type of indicating system that's used in this particular case to tell you about the flap position. Let's take a look at a graphic of one type of synchro system, which is a DC Selson system. On the DC Selson system, you've got a transmitter over here on the left, you've got an indicator over here on the right, and basically the reason they call it a synchro system is synchro is short for synchronous, and it means that the indicator in the cockpit is going to move exactly the same amount as the transmitter is. So basically it's an electrical method of indicating a remote mechanical movement or position, and it does it by the indicator moving in synchronous with the transmitter moving exactly the same amount. Now, some of the things that you can use a DC Selson system to indicate are the position of retractable landing gear, the position of wing flaps, the position of cowl flaps, our oil cooler door positions, and in some systems, depending on the type of gauges, to indicate fuel quantity. Now, another type of synchro gauge that will tell you about flap position and similar things is the Magnuson system. The Magnuson system operates almost identical to the DC Selson system. The difference is the rotor. The rotor in a Magnuson remote indicating system uses a permanent magnet in that rotor system. Now, another very similar system is the autosyn system. The autosyn system, the difference between it and the magnesin system is in the rotor, because in an autosyn system, the rotor is an electromagnet. So basically, the difference between these three is in the rotor system. Okay, let's talk about the autopilot system on the aircraft. The primary purpose of the autopilot is to relieve the pilot of control of the aircraft for long periods of flight. You get fatigued just having to pay close attention to the controls all the time, and so you turn it over to George here and let the autopilot do it. Now, if you have a fully integrated autopilot in the aircraft, fully integrated means that the autopilot can control the aircraft around 3 axes. It's going to be able to control the bank, the pitch, and also the yaw. Fully integrated controls it around 3 axes of movement. Now, in an electromechanical autopilot system, the sensing device is a gyro. So what's happening is the gyro is sensing what's going on in the aircraft, and it's giving information to the autopilot. It's the relative motion between a gyro and its supporting system that's the operating principle for the sensing device used in the autopilot system. For instance, the sensing element, one of the sensing elements of the autopilot system is an attitude indicator. They'll ask you, an attitude indicator is what kind of element of an autopilot system, and it's part of the sensing element of the autopilot system, because the gyro and the attitude indicator is telling the autopilot what's actually happening in the aircraft. Now, you want to operationally check an autopilot system on the ground. A lot of times you do that for maintenance, and the pilot does before he flies it. But you don't want to do it until after the aircraft's main power has been switched on and the gyros have come up to speed and the autopilot amplifier has warmed up. Then and only then do you want to go ahead and engage the autopilot, because you want to make the gyros are up to speed and the amplifier is warmed up before you engage the autopilot. Now, the component of an autopilot that moves the control surfaces is a servo motor. The servo motor applies torque to actually move the control surfaces of an aircraft to make the aircraft do what the autopilot is commanding. The channel that detects changes in pitch attitude and controls the aircraft in pitch is the elevator channel of the autopilot. The elevator channel will detect changes in pitch attitude, and it controls the aircraft about the lateral axis. The lateral axis is the one that goes from wingtip to wingtip, and the aircraft pitches around the lateral axis, and that's controlled by the elevator channel on the autopilot. Now, in the autopilot system, you've got displacement follow-up systems, and the displacement follow-up develops and transmits a negative feedback signal. And what that does, the follow-up signal in the autopilot, this displacement follow-up signal, nullifies the input signal, for instance, to the ailerons. And what that means is that when the autopilot commands the ailerons to displace to bank the aircraft, that follow-up signal will then nullify the input and bring the ailerons back to the neutral position. Now, let's assume that the aircraft has deviated from attitude or heading, and the autopilot system has changed the attitude or heading in order to correct for that deviation. But the control surfaces are returned to neutral after the aircraft has returned to its correct position instead of before. What kind of result are you going to get? What you're going to get in that case is an overshoot and some oscillation. There needs to be some anticipation in the autopilot system, because if you wait until after the aircraft is actually back in the correct position, you're going to actually end up overshooting where you want to be, and you get overshoot and oscillation. Now the FAA will be asking you what part of the autopilot system allows you to manually control the aircraft while you have the autopilot engaged, and that is the flight controller. Not servos and other parts of it, but it is the flight controller that allows you to manually maneuver the aircraft while the autopilot is engaged. Now, if you have large modern aircraft, and a 747 is certainly large and modern, the flight management computer will monitor the flight parameters of the aircraft and perform autopilot functions. It is a much fancier autopilot. The autopilot function is just one of the things that the flight management computer will be doing. Now, when you have jet aircraft like this, notice how swept back those wings are. When you have very swept back wings like that in a jet, one of the things that you will tend to get is Dutch roll. This is what Dutch roll will look like. It's kind of a rolling and yawing oscillation, and as you can imagine, it is a very unpleasant sensation. It occurs particularly with swept wing aircraft. How do you counteract that Dutch roll, yawing and rolling oscillation? What you use is a yaw damper system, and this is the control unit on a yaw damper system to get rid of that Dutch roll oscillation. Let's talk about warning systems, and first of all, let's talk about takeoff warning systems. The whole idea of a takeoff warning system is that when the pilot puts the throttles forward to start the takeoff roll, this warning system will monitor certain items in the aircraft and announce to the pilot with lots of lights and loud horns if these different items are not set properly in the positions, in the ranges for takeoff. So the takeoff warning system is going to monitor, first of all, the throttle setting, because it's the movement of the throttles going forward by the pilot that tells the system to monitor these other things and set off alarms if they're not set right. The warning system will monitor the position of the elevators. It's going to be checking elevator trim. Is it in the takeoff range? It's going to be checking the speed brakes because you want them at 0 for takeoff. You only want speed brakes out when you're landing or trying to slow down, not when you're doing a takeoff. It will monitor the position of the flaps to make sure that the flaps are in the takeoff range, and also stabilizer trim to make sure that it's in the takeoff range. What it does not monitor is the ailerons and the position of any aerodynamically actuated slats. If they are aerodynamically actuated, that means that the pilot has no control over them and they'll just do their thing when they need to. So those are not monitored, and the ailerons are not monitored. Now, the takeoff warning system, you need to know, is actuated by the closing of the thrust lever switch. All that means is that when the pilot put the throttles forward, he closed a micro switch on the throttle quadrant, and by closing that micro switch, he actuated this takeoff warning system and started it monitoring all those different parameters. Another type, a different type of warning, might come up on an instrument, such as a horizontal situation indicator, or HSI, red flags for nav or heading or glide slope. And you need to know that when a red flag shows up like that, it means that that particular function is not operative. The function is inoperative. It does not mean you've deviated from what you want to do. It means that function is not working. You could have a red nav flag only, which means that the heading is working fine, but you have no navigation reception on the indicator. If you have both of them, it means you not only don't have any navigation information, you don't have any heading information either. The function is inoperative. It is not working. And that's what you need to know about aircraft instrument systems.